basically we have, I think, looking at semiconductors. I think semiconductivity. I think yesterday we have, I think, elaborate slightly, not to detail, about the different types of semiconductors. But then again, it's just a brief introduction that for semiconductivity, we have intrinsic semiconductors and also extrinsic semiconductors. What does it mean by intrinsic semiconductors is that this type of semiconductors can be defined by electronic structures that have a pure material. So pure material means that the semiconductor is mainly built or produced from one types of element. For example, silicon, germanium. Normally, these intrinsic semiconductors are coming from group 4A elements. So that is why you can see silicon, germanium, and whatsoever. And apart from that, okay, there's also compound semiconductors that can also be considered as intrinsic semiconductors, which normally coming from the combination of group 3 until group 5. So you have gallium arsenic, indium, antimony, and whatsoever. Meanwhile, for extrinsic semiconductors, it means that this electrical conductivity is defined by impurities of atom. Okay, so impurities of atom means that you have, I think, a group 4A materials, like for example, silicon doped with elements from group 5A and 3A. Okay, then we can also have different types of extrinsic semiconductors named as N-type and also P-type. And what does it mean by N-type and P-type semiconductors? Okay, again, N-type, it means that this type of semiconductors, okay, you have an excess, you have more free electrons. You have N, you have N rather than P, because P is actually considered as whole. And P-type is actually elements from group 4A doped with group 3A. For example, silicon doped with aluminium, boron, gallium, and whatsoever. So in this case, P-type means that this type of semiconductors have less electron, and when you have less electron, this actually create holes. Okay, so that is why I guess over here it should be noticed that for N-type, okay, oh sorry, I haven't connected this one. Okay. So for N-type, basically this will have N bigger than P. Meanwhile, for P-type, you have P bigger than N. Okay, N bigger than P means that you have more electrons, more free electrons than whole. And P more than N means that you have more holes. Okay, as compared to the free electrons. We also have to understand what does it mean by free electrons and also hole. Free electron, it means that the electron that is produced, okay, from the promoted electron from valence band into conduction band. And when you have, I think, a movement or a promotion from one electron from valence band to conduction band, this will leave a hole, which could be positively charged. So this is always in the case of intrinsic semiconductors, where the number of free electrons is equal to the number of holes. Okay. So this actually in the case of if you have only silicon as your material, silicon bonded with another neighboring silicon. Okay, so when applied electrical field is given, so you will have promotion and electron will move to conduction band and will produce a free electrons and also holes. Right. So electrical conductivity for intrinsic semiconductors can be summarized as follow. Sigma is equal to n multiplied with the magnitude of electron, modulus E, okay, multiplied with mu E, plus P is a number of hole multiplied with modulus E multiplied with mu H. Okay, so for today, I think it's just another detailed discussion on extrinsic semiconductors, where, as I said earlier, extrinsic semiconductors, it means that the electrical conductivity of this material is being defined by the inclusion of impurities atoms coming from group 5A and also 3A. Okay, for example, consider silicon. Okay, consider silicon to be extrinsic at room temperature if impurity concentration is 1 atom per 10 power of 12. Okay. Remember, estimate number of electron promoted to conduction band at 300 Kelvin. Unlike intrinsic semiconductor, extrinsic semiconductors may have different concentrations of hole and also electrons. So concentration means that different amounts. So P-type, it will be P-type if holes is bigger than free electrons, and it will be N-type if the number of free electrons is bigger than number of holes. This is what I have explained earlier just now. Okay. So doping, what does it mean by doping? Doping ni bukan yang cek kencing tu kan. There's also different meaning. So doping, it means that you dope, you add small amount of impurities into your material. So part of the examples of method for doping is actually diffusion and ion implantation. Okay. Extrinsic electron carriers, it produced by substitutional impurities that have more valence electron per atom than semiconductors matrix. For example, phosphorus. Phosphorus with 5 valence electron. Phosphorus is one of the elements in group 5A. Okay. It has 5 valence electron, then it is an electron donor. So why it is electron donor? If you still remember the diagram that I sketched earlier, if phosphorus is been doped with silicon, so you have silicon, phosphorus, and one phosphorus over here. Okay, you will notice that okay, 2, 3, 4, 5. The one that I put X is assumed as the valence electron of phosphorus. You'll see that 1, 2, 3, 4. 4 of from phosphorus valence electron forming a bonding with silicon, and it has 1 excess. Okay, so this excess is known as electron donor, or can be categorized as a free electron. Understood? All right. So fifth outer electron of phosphorus is weakly bound in donor state. It can easily promoted to conduction band. Phosphorus is a donor impurity, and the impurity which produce extra conduction electrons are called donors. Okay, so ND. Okay, number of electron could be considered as ND lah, donor. Okay, element in column 5 and 6 of periodic tables are donors of semiconductors in column 4. So if you have silicon bonded with phosphorus, bonded with group from, element from group 6, this can be considered as N-type semiconductors. Okay. So how does it possible for N-type semiconductor to be produced? Because you can see that the valence band over here. So valence band, okay, remember if let's say that it has been used to bond to form to bind to form a bonding, then most of this electron will be used up. Then you will have an excess. The excess electron is actually located not inside the conduction band, but it is actually located outside the valence band. Macam ni lah. Nampak ni. Dia just floating outside. Not, I think, involving in the bonding of electrons or elements. And then what happens is when you apply electric field, electric field is applied, then what happens is that this donor's electron or the free electrons can easily goes into the conduction band. Okay. Therefore, what will be the conductivity for n-type semiconductors? For n-type semiconductors, conductivity is equals to ND, number of a donor electrons multiplied with modulus E, magnitudes of E, multiplied with mu E. Okay, so modulus E over here is equals to 1.9 times 10 power of, 1.6 times 10 power of 90 coulombs. Okay, all right. And you might ask me, why actually in this case, there's no holes being considered? As I said, for n-type semiconductors, we know that n is larger than p. Okay, if we look at intrinsic semiconductor, okay, the formula of conductivity is equals to n multiplied with modulus E multiplied with mu E plus with P multiplied with E multiplied with mu H. So why there's no of this component? Because when we say that in the case of n-type, this will be negligible. It will be neglected. Okay? All right. Moving on to p-type. Okay? So p-type, it means that you have excess holes. Okay? Tak cukup elektron. Substitutional impurities that have fewer valence electrons per atom than matrix. Okay? I guess in the case of our example, you have boron. Okay, so boron is actually in group 3. Okay, in group 3. Of course, if you look at the valence electron, okay, sorry, not this one. Okay, should be this one, and this one only. Okay, so you have one, I think, unoccupied electrons to form a bonding. So another neighboring silicon is floating. It didn't form any bonding with boron. Okay, so in this case, it forms a holes. Okay, so holes, okay, is a weakly bonded to the impurity atom. Normally, p-type will be formed if you have group 4, okay, combined with group 3. Okay, in this case, you will have a so-called acceptors rather than donors, Na. Right. So in this case, what's going to happen is that in the valence band, you have, for example, here 3 electrons been put. And then when the applied electrical field is, I think, produced, then what happened is that it didn't go into the conduction band, but it's just like promoted slightly into the band gap or slightly above valence band. Slightly above valence band. Okay, all right. So in this case, you will have more holes than number of electrons, free electrons. Then the conductivity, okay, is equals to Na acceptors multiply with modulus E multiply with mu H. Okay, all right. So this is actually the summary between intrinsic semiconductors and extrinsic semiconductors. Okay, so maybe based on this summary, I just want you guys to explain a bit, like what did you guys understand? Maybe perhaps in the forms of some, I don't know, maybe some graphics or some flow chart or some mind map or what, that I will put up in the e-learning as a homework for you guys to discuss or differentiate between intrinsic semiconductors and also extrinsic semiconductors. Okay? All right. So again, as I told you, intrinsic semiconductors is always related with the pure element. Okay? Right. Number of holes is always equals to number of electrons. Extrinsic semiconductors, this is actually with regards to the impurities, presence of impurity in the material. Then the number of electron is not going to be the same as the number of holes. You also can have n-type and p-type, where n-type it means that you have more holes than, sorry, n-type means that you have more electrons, more n compared to holes. P-type it means that you have more holes than electrons. Okay, and this is actually the formula for conductivity, n-type, and this is for p-type. Right. Can we have a very quick examples of, I think, semiconductivity? So consider this figure. So you have a figure of mobility versus doping concentration at the temperature of 300. To high purity of silicon is added 10 power of 13 centimeter cube aluminum atoms. Number one, is this material n-type or p-type? Please explain. Yang ni saya nak minta someone to give a opinion, answer. Amelia ada? Shanas? Amelia Shanas? Ada tak? Amelia? Amelia tak ada. Okey. Ani Zulaika. Ani Zulaika 2, Ani Zulaika 3 pun tak ada. Okey. Gui King Sheng. King Sheng, are you there?
P-type.
P-type. Can you explain why P-type?
Because aluminium is in group 3. Because aluminium is in group 3 and silicon is group 4.
Okay, all right. So the most important thing to answer question number 1 is to indicate, okay, the dopant coming from which group. So I think Kin Sheng have give a very good explanation. Okay, he says that aluminium is actually from group 3. Oops, apa ni? Okay, nak tulis A jadi V pula. Okay, 3A. Right. So when you position this element into group 3A, you know that in group 3A, is it going to be have an excess of electron or less electron? Of course, it will have less electron. Then this could be considered as acceptors rather than donors. Okay. Then this one, I think to answer number 1, it is actually P-type. Reason is because, as I said, it is, the aluminium, the dopant is actually from group 3A, okay, where you have a less of electron and possibility of having more acceptors rather than donors. Okay. So number 2, question number 2. Calculate the electrical conductivity of this material at 300 Kelvin, given that modulus E is equals to 1.6 times 10 power of minus 19 coulombs. So what information that is needed in order to calculate I think apa tu? Conductivity. Sekejap, cari nama. Izzat. Izzat ada Izzat. Izzat Nazri. Izzat Nazri. Tak ada. Okey. Muhammad Hakim. Azhan. Muhammad Hakim ada Muhammad Hakim? Semua pakai bisu Oh, semua dah jadi bisu. Okey. Right. Nur Adriana. Nur Adriana. Adriana.
Doktor.
Okey. Ada juga Adriana penyelamat. Okey. So, Adriana, if you want to answer question number 2, so what do you think information needed from figure 1? Sebab dia cakap consider figure 1. So, it must actually meaning something.
Mobility.
Nak kena check mobility. Tapi kalau, if you look into this figure, there's two curve. Ada tulis electron and also holes. So in order to find the mobility, okay, because you know that the doping concentration is given. Doping concentration is given as, alamak, kat sini dia off range pula. Okay, katakanlah saya tukarlah sini, not 13, 14 lah, atau 14 lah, ataupun not 14 lah, kita ambil yang susah sikit, 17 lah, for example 17. Okay, 17. So which curve that actually you are looking at?
Electrons.
Electron. Okay, Adriana cakap electron, betul minta mat
Yeah.
Okay, alright. I just need another opinion from, terima kasih Adriana Okay, so I need another opinion. How about Nurul Nazrin? Nazrin? Tak ada. Okay. Siti Nurhana.
Ya, doktor.
Okay, alright. So, Adriana cakap tengok pada curve electrons. You think that you agree or you have your own opinion? Ke macam mana?
Saya rasa dia tengok dekat electrons juga.
Kat elektron juga. Okay, alright. Okay. So, terima kasih. I think last one I would like to ask from Tan Shi Leong. Tan Shi Leong?
Yes, doctor.
Okay. So, are you agree with your friend, two of your friends, saying that you have to look at electron curve?
No.
Okay? Or you have your own opinion?
The hole's mobility.
Okay. So, why actually you say that we have to look at the hole's mobility? I mean the hole's curve.
Because this is the P-type material.
Okay. All right. Then, in order to maybe to find the value of mobility, mu, we have to look into the most related one. If it is a p-type, then we are looking at mu h. If it is an n-type, then we are looking at mu e. So mu e is electron mobility. Okay, mu h is actually hole's mobility. So in this case, we are looking at the hole's mobility at 10 power of 17 over here. Okay. So you get a value around maybe 200. Let's say 200. Okay, unit is given. So Shi Leong, how you can calculate the conductivity? What's the formula?
N, the number of holes, times modulus E.
NA or ND?
NA.
Multiply with modulus E, multiply with
Mu
H.
uh,
Okay. All right. So it should be 1 times 10 power of 17 multiplied with 1.6 times 10 power of minus 19 times 200. You will get the answer over here. Okay? All right. So I hope that it is quite clear with everyone. And this kind of question is normally being asked probably later on during your maybe exams, tests, or quiz. So it is important to understand if you want to produce a semiconductor and if you want to categorize it, you should know what it will be the dopant. If you have a doping, okay, then it will be extrinsic semiconductors, and the types of dopant, if it is from group 3, okay, then it will be P-type. If it is from group 5 or group 6, then it is N-type. All right. So extrinsic and semiconductors conductivity versus temperature. Data for doped silicon. Conductivity will increase if the doping is increased. Okay. Reason is because imperfection sites lower the activation energy to produce mobile electrons. And the comparison between intrinsic versus extrinsic semiconductors, I guess this one you can also discuss it in your homework later on. Okay, extrinsic doping level. Okay, with regards to if the amount is around 10 power of 21 of an N-type purity. Okay, then if the temperature is lower than 100 Kelvin, then this will be considered as a freeze-out state where the thermal energy is sufficient to excite electrons. If it is in between 150 Kelvin to 450 Kelvin, then this is extrinsic. And if it is greater than 450 Kelvin, then this could be considered as mainly intrinsic. Okay. Right. So temperature variations of conductivity. So we just want to see if we increase the temperature, what will be the resultant conductivity. Okay. Basic equation for conductivity of intrinsic semiconductor is noted as this. Okay. Strong exponential dependence of carrier concentration in intrinsic semiconductors. Temperature dependence of mobility is weaker. Right? So if you have a plot between conductivity of holes or number of electrons versus 1 over temperature, this produces a straight line. Okay, so from this straight line, actually you can calculate the gap energy. Actually, you can use this plot. Okay, if you have like ln, how to say ln p or ln sigma log or what versus 1p, 1 over t. This actually could be related with Arrhenius equation, which in the end of the day, if you assume it as linear, then you can calculate the slope. Then the slope, it will be equals to the gap energy. So this is actually important. Okay, when you produce a material, when you put the doping and whatsoever, you might question what will be the gap energy. So the gap energy of your mixture of your semiconductors can be calculated after you conducted thermodynamic studies. You studied the conductivity behavior at different temperature. Then when you do the plotting, you calculate the slope and whatsoever, you assume the linear equation as Arrhenius equation, the slope is actually equals to the gap energy. Temperature variation of a conductivity for extrinsic semiconductors. Okay, at low temperature, all carriers due to the extrinsic excitation. Medium temperature, most of the dopant will be ionized. This is where saturation I think happens. And finally, at a higher temperature, intrinsic generation of a carrier will be dominates. Okay, so moving on. Now we are looking at conduction in other types of materials, not I think in semiconductors, but I think in other materials like, for example, polymers or ionic materials. Okay. So for ionic materials, the band gap is large and only very few electrons can be promoted to the valence band by thermal fluctuation. Cations and anion diffusion can be directed by the electrical field and can be contribute to total conductivity. So the conductivity of ionic materials will be related to the effects of electronic or electrical field, as well as the ionic diffusion. Higher temperature will produce so-called Frankel and Schottky defects. This one also you have learned it, I think in chapter 4 or chapter 3 with Dr. Chua. Okay, so Frankel and Schottky actually explain the arrangement, okay, of a material in a lattice, okay, where you can have like impurities, substitutional or interstitial. Okay. Meanwhile, for polymers, the conduction, polymers are typically not conducting. It is a good insulator, but it can be made conducting by doping. So that is why you might heard about polymer electrolyte, where you have polymer or plastic plus with, I think, salts or conducting salts. For example, lithium salts, sodium salts, potassium salts, or whatsoever. Normally, all this will give a very good conductivity. A few polymers have a very high electrical conductivity, about 1/4 to the F copper, or about twice to the F copper per unit weight. So, conducting is polymer, okay, not similar as polymer electrolyte. Polymer electrolyte, you have polymer doped with salts, but some conducting polymers, as I mentioned, polyaniline, okay, polypyrrole, okay. All these are actually polymers that can behave as a conducting polymer. It has a good, I think, conductivity values because looking at the structure of polyaniline or polypyrrole, it can actually have this resonance, electron resonance stabilization, where electrons can be moved from one end to another end. So that is why this polymer can be considered as conducting. Comparison between polymers and ionic materials, you can see the range. If you compare it as well with materials such as metal, wood, non-metal, whatsoever. Okay, polymers, of course, it will be lower conductivity, having a conductivity that is lower. Okay, metal normally have a very high. Okay, semiconductors will be in between. So you see silicon, germanium. So this part of the intrinsic semiconductors. So it will be located in this region. So this, I think, region in the middle is basically this one is basically semiconductors. This one is all insulators. And this one is conductors. Okay, so there's a few last slides before we end our topic for today. Dielectric materials. A dielectric materials is an insulator. Initially, it is not conducting. It is insulator in which electric dipoles are induced by electric field, okay, or permanent dipoles that can exist even without electric field. That is where positive and negative charge are separated okay, on the atomic or molecular level. So initially, this insulator, it has positive pole and negative pole. It has charge, positive charge and negative charge. But it is not, I think, having a moment. We call it as a dipole moment. So when you apply, okay, electrical field, what happens is that this material will form a so-called dipole moment. You have a positive charge at one end and negative charge at one end. So this moment can actually create a so-called dielectric effect. So the magnetic of the dipole moment is equals to P equals to QD. Okay, D is actually the distance and Q is actually the current, or the charge. Dielectric materials are used in capacitor to store the electrical energy. So mostly capacitors, capacitor is not really conducting. It can store energy, and when you apply electric field, it can actually produce whatever it has been stored. Capacitance and polarization. Capacitance is related to the charge stored. Okay, Q between the two oppositely charged layer subjected to a voltage. So capacitance is equal to charge over potential. And capacitance is also defined as the ability of a material to store charge. When voltage is applied, okay, to parallel conducting plates, what happens is that the plates will be charged by positive charge and also negative charge. As a result, this electrical field will develop between the two plates. And charge can remain even after the voltage has been removed. So you actually assume you have a material that initially it is not charged, but when you actually apply the potential, it will become charged and it can, remain charged even after you stop the supply. So part of the best example is your battery, your phone battery. So your phone actually will have the if it is not charged, then of course you tak ada battery lah, zero charge. So when you charge, it will store. It will be, producing, the moment or the stored charge. And after you have, dia dah penuh, after it reach 100%, then when you stop the charging, you'll see that your phone still can function because it's still, the material is still have its own charge. Okay, so capacitance depends on the geometry of the plates and the material between the plates. Okay, all right. Last few slides. Capacitance and polarizations also. The orientation of a dipole along the applied electrical field called polarization. Orientation. So the orientation between the dipole is called polarization. It causes charge density to increase over that of a vacuum due to the presence of the dielectric material. So that D is dielectric displacement equals to epsilon naught. So epsilon naught is basically your permittivity in vacuum. Okay, plus with P, where epsilon is electric field. Okay, D is surface charge density of a capacitor, also called dielectric displacement. I think maybe if you don't really understand about this one, it's okay. It's just an explanation of how you can actually produce dielectric displacement. Okay, and what does it mean by polarization? Polarization is actually the effect after you do dielectric displacement. So the mechanism of polarization, it could be in several ways. The one that we've seen just now is that you have a material, you charge it, and then after that you uncharge. So there's also another methods. The first one is known as electronic polarization or induced. This is actually due to the displacement of the center of the electron cloud around the nucleus under the electric field. Okay. Second, ionic polarization. This is also an induced technique. Okay. Any induced, what does it mean by induced? Induced means that you apply, you give a supply to the material. Kita bagi macam contoh, you put current or you put potential into the materials. So this actually means by induced. Ionic polarization, it occurs in ionic material as the applied electric field displays the cation and anion in opposite direction, resulting in a net dipole moment. Okay, so next we also have molecular polarization. So this is more of like orientational, that can occur only in materials having permanent dipole moment. The materials that already have permanent dipole moments is not mean that the material doesn't have any moment. For the first two mechanism, okay, we assume that the material it is ionic, but it doesn't have dipole moments. Okay, so that is why you need to induce it. But this material actually have its own permanent dipole moment. For example, like magnets and whatsoever. And then the rotation of the permanent moments in the direction of the applied field causes the polarization in this case. And finally, we have a so-called space charge polarization arises from accumulation of charge at interfaces in the heterogeneous materials consisting of more than one phase having different resistivity. Okay, so this is actually to show you the difference between electronic polarization, ionic polarization, and orientation polarization. As I said, for electronic polarization, when there is no, I think maybe over here we can just separate it. Okay, so this means that there is no applied potential. So this one, it means that there is applied potential. So for electronic polarization, when there is no applied potential, you will see that the material is like that. It has a charge, but it cannot produce anything dielectric or whatsoever. But when you apply potential, so it will produce this dipole moment, and then this will give the effect of dielectric. So when you have dielectric displacement, then you will have polarization. Okay, so ionic polarization is the same thing. Okay, so ionic polarization, initially you'll see that the ions is already there. Okay, so when you actually apply electric field, so it is just producing the same thing, but you'll see that the electron still can mobilize because it's already in ionic state. And finally, for molecular orientation or polarization, this one initially you have materials that have a permanent, permanent charge. Okay? Then when you apply the potential, the orientation of the movement of the electron will be organized, more organized. It will goes into one direction. Ferroelectricity, perhaps just a simple definition. It is defined as the spontaneous alignment of electric dipoles in absence of external field. Spontaneous polarization results from relative displacement of cation and anions from their symmetrical position. Okay, ferroelectric poses a permanent dipole. So, for examples, you have barium titanium oxide, Rochelle salts, potassium dihydrogen sulfate, potassium niobate, lead zinc chronate, titaniate, and whatsoever. So these materials have extremely high dielectric constants at relatively low applied field frequencies. Hence, capacitors made from ferroelectric material are smaller than those made from other dielectric materials. Piezoelectric materials. Okay, this one actually quite special because it is actually relating a material that when you apply mechanical stress, it will actually produce electrical energy. So piezoelectricity always related with materials. Okay, materials that you apply stress, which it will result this electric energy. Okay, it arises due to the polarization induced by external force, thus reversing the direction of external force. The direction of the established field can be reversed. Okay, the application of an external electric field alters the net dipole length, causing the dimensional charge. Application of this material includes microphones, okay, ultrasonic generators, sonar detectors, and mechanical strain gauge. For example, you have barium titanate, lead titanate, lead zinconate, aluminium dihydrogen phosphate, and quartz. So all these are actually the examples of piezoelectric materials. So you can find, I think, examples in YouTube. For example, if you type piezoelectricity materials, you will see that there's material that when you push, we just push, push, it will produce like, it will glow the LED lights. So this is the technology. So as a summary, what we have learned from this chapter, we have understand what does it mean by conductivity, resistivity, okay, how actually materials can produce conducting materials. What will be the category? You have conductors, semiconductors, and also insulators. The definition of electronic conduction by energy band diagram, okay, and then for conductivity, you have intrinsic semiconductors, extrinsic semiconductors, P-type, N-type, and I think other electrical characteristics which will be quite minimal on ferroelectricity and also piezoelectricity. Right. So I guess that's wrap up our chapter 10B, the electrical properties. Is there any questions so far that you would like to ask? Anything that you want to ask, maybe regarding on your assignments and whatsoever? So inshallah, next week we are going to start with another chapter, magnetic properties, okay? And we try to finish off all the remaining chapters. I don't know. Now is week what? 11 or week 10? I don't know. Week 11 maybe. So we still have like maybe 3 weeks time before we end. So hopefully we can manage to finish the whole things. All right. So any question? As always, I will stay back for a few minutes if you have any question. But those who doesn't have any question, I would like to thank you guys. Thank you very much for your kind attention. And I hope to see you guys next week, Monday. And your quiz. There's no quiz for today, yeah? No quiz for today. We are going to postpone your quiz next week. So next week quiz will be in combination with magnetic properties. Right. So with that, thank you very much. And have a good weekend. Assalamualaikum warahmatullahi wabarakatuh. Bye.
Thank you, Dr.
Welcome.